Good morning. Normandy University. It's my great pleasure and honor to introduce to you Professor Simone Hochgreb from Cambridge University. As you certainly know, in the field of turbulent combustion, it's easy to find someone for performing simulations, desperately trying to simulate experimental results and reproducing them. But it's very challenging to find someone producing those experimental results. And Simone is one of them. So she has developed measurements and analysis method for autoignition, premixed turbulent flames, sprays, soot and particle formation, as well as thermoacoustics. Her more recent interests are in the application of optical diagnostics to the measurements of temperature and species in turbulent flames, thermoacoustics, aerosols, and flame synthesis. Prior to Cambridge, she held position at MIT in the US, Sandia National Labs. She held a Bachelor in Mechanical Engineering from the University of Sao Paulo, Brazil, and PhD in Mechanical and Aerospace Engineering from Princeton University. She's a Fellow of the Royal Society and Fellow of the Combustion Institute. She has received the Wolston Merit Award and the Society of Automotive Engineers Ralph R. Titer Award. Simone, the floor is yours.
Thank you, Luc, for the very kind remarks. And of course, I'm very honored to have been asked by the program chair, so thanks very much, Niels and Benedict, of thinking about me to talk to you about it. It's always very challenging to be the last one in a roster that had such excellent presentations as we saw this week. Even more challenging when it's the last day, everybody's tired and thinking, can I do one more day of combustion talks? For those of you who think, well, everything has been done, I give up, I hope to show you that we only at the beginning of really understanding a lot of topics that are really important to what we're going to do next in combustion. I was asked to talk about gas phase combustion, and of course this is a huge topic, so what am I going to do? But I was thinking about what we're going to do in the future, so we're thinking about new fuels, hydrogen, and so on, and what's important then. And I went down this rabbit hole from which I learned a lot, and I'll try to connect the dots for you about how laminar flames behave and how turbulent flames with these different fuels might behave. So that's the title of my talk, but the original placeholder title was How Fast Can We Burn 2.0? And some of you may have seen the title on social media, and I was a little bit alarmed because that was just my placeholder title, not the official one. And that was because I was inspired by a talk that was given 30 years ago by Derek Bradley, who's still going strong, 93, still gives me a lot of advice and a lot of grief. Wonderful man, and he gave a talk called How Fast Can We Burn in 1992, the symposium, and which was very much about understanding turbulent flames and turbulent flows. So I won't do a review of the last 30 years necessarily, but it will touch on many of the aspects which are still not resolved. Okay, where does this fit into our universe of combustion in real devices? As we know, combustion problems come in all shapes and sizes. We might have autoignition, high pressure, sprays, soot, NOx, and so on, and we have all these wonderful sessions here where we talk about all the different problems which are relevant to gas turbines, to IC engines, and to furnaces. All of these may or may not be premixed. They have solid particles, they have thermoacoustic instabilities, they have sprays, and so on. But mostly all of them are trying to deliver hot gas in some form, typically as cleanly as possible, but that is, of course, a little harder than we think. I thought about doing a review of everything that has been done on that, but it has been done by Asad Masri, I think at the last symposium, and there was also a panel in the Dublin symposium, so I thought maybe I'll just focus on something that is dear to my heart, which are premixed flames. And you might say, don't we know everything about premixed flames? They're so easy, right? Well, so I thought, but as you dig more about it, then you see that things are not so simple, and there are many answers that we don't have. Of course, premixed flames themselves have a lot of applications. We're always trying to make flames more premixed, because if you premix flames, temperatures are lower, you don't produce pockets of high temperatures, and therefore NOx is lower, so that's all a good thing. And so whether it's internal combustion engines or in industrial combustors, we're always trying to make them a little bit more premixed. But there are limitations to that, typically associated with either keeping the flame stable or burning a little faster, and there will be technically premixed flames that don't operate fully premixed. But what I talk about today will be relevant also to flames that are, for example, stratified. But that's not the direct topic of the flow. Okay. The other reason why I wanted to talk about premixed flames is that now we're, as we've seen in this meeting, we're talking about unusual fuel mixtures, be it hydrogen, ammonia, ammonia on its own, and mixes thereof with hydrocarbons. What I'm showing here is a little flame ball scanned in 3D, and I'll come back to that topic a little bit later on, by the group at Leeds, where you see it growing, and you have this nice, smooth, turbulent flame, I think for the first time measured in 3D. And if you compare that to what happens to a hydrogen flame under similar conditions but at high pressure, you can see that the rate of growth of this flame ball is stonkingly high, and the flame looks quite different. It has all these tiny little structures. And that is not very well understood, but we need to understand it because we will be burning hydrogen. Well, we have been burning hydrogen in rockets, of course, in a slightly different way, but we may be doing a lot more of that in the future. So in order to understand that, we need to dig back into the fundamentals of how these flames behave. But one of the things that is known is that lean hydrogen burning is very sensitive to turbulence. And even for usual hydrocarbons, as I found, and if you dig through that, turbulent burning rates depend on more than just the laminar flame speed and the turbulence levels. And what that is the topic of this talk. So I'll talk about first measuring the laminar flame speed. I'm experimentalist primarily, and therefore I'll start with the measurements of something that I understand a little bit better. And then we'll have a little diversion on intrinsic flame instabilities. Then we'll talk about measuring turbulent flame speeds and how we're doing on that front. And then I'll try to put everything together on the relationship between those flame speeds and molecular diffusivity. So on to measuring laminar flame speeds. I'll talk about two different methods which are the most popular for measuring laminar flame speeds, and they'll also illustrate what happens to flames when they are exposed to a flow field. One method is to try to stabilize a flame which is reasonably flat. And you do that by having twin flames which are opposed, and then you can create a nice flat flame which is stabilized. One of the things that will happen, and that was introduced by Ed Law in the 1980s, and he's been really the primary developer of many of the theories and experiments in this area. So when you put the flame then in this aerodynamic field, then the flame will experience stretch, which means its area will be experiencing an extension. And that can be decomposed into a tangential stretch and a curvature stretch. So one of them is just pulling the flame like a flat piece of plastic, and the other one is bending the flame like a little balloon. In these flat flames here, we don't have curvature, so we just have the tangential stretch. And typically the way that we measure these flame speeds is we measure, for example, with particle image velocimetry. I have a velocity field. We're showing here just the half of the top or the bottom flame. Then we can measure the flow field, and from the gradient of velocity, we can then obtain the strain rate. Now that we have the strain rate, we can obtain along the center line the axial velocity as a function of distance from the nozzle. And at some point, the velocity of the field will go down, and at some point the flame sits there, and obviously there'll be an acceleration of the flame. And that's a reference flame, which is used to work out and compare that to kinetic models. So we can have a map of this reference flame as a function of the strain. Next, I'll walk you through what happens when you strain the flame, what should happen to the burning rate at the location of the flame. And a lot of this analysis here, I'll try to compress about 30 years of analysis into one slide, sorry. The idea here is that if you have profiles along the central line of fuel or oxygen flow, which disappear into the reaction zone, which is marked in blue there, and then we have a preheat zone, which is marked in yellow in 2D. And we see the temperature going up in the other direction. So that's pretty straightforward. If you try to do an analysis there of the mass conservation in the yellow box, obviously the streamlines are diverging, so some of the mass will disappear. And if we define now a density-weighted stretch, and that's a concept which I owe to Jérôme van Ooyen, a very clear paper on the topic, then we can just think about it as by mass conservation, there will be mass rate loss through the sides because the streamlines are diverging and I have a stretch. So what comes in is slightly different than what goes out, and that proportionality constant, that difference is proportional then to stretch. Of course, if the lines went the other way, not in the situation, but it can happen, for example, in a Bunsen flame where you might have streamlines converging, that you have a gain of mass rather than loss. But let's stick with this analysis for the moment. If you think about all the other scalar fluxes, for example, the enthalpy flux or the species flux that will be carried, they also will be lost through the edges. But, and of course, that would depend on the profile of temperature or species or any other factors that you have. They will be lost either at the same rate if they have exactly the same non-dimensional profile, or at a different rate if not. Now, the second thing that happens with flames in a simplified picture is that when you have the interface between the reacting zone, which is the blue one, and the preheating zone, is that there's a match there between the heat produced and the heat diffused into the preheat zone, or conversely, it could be all the fuel coming into the preheat zone without reacting and the amount reacted in the reaction zone. So there always has to be this matching of the diffusive and the reactive on one side and the diffusive and convective on the preheat side. Now, if I'm stretching this flame and there's no difference in diffusion between mass and heat, then the profile should stay self-similar and everything is lost at the same rate, and therefore the impact on the flame will just be from that loss of everything at the same rate. But if the fuel diffuses at a different rate from temperature, for example, or whatever is the limiting species, it could be oxygen diffuses at a different rate, then the profiles will need to adjust themselves in order to obey this matching condition. And we define that by taking the diffusivity as being this lambda over OCP, then divided by the Lewis number. The Lewis number is the ratio of the diffusivity, the thermal diffusivity, to that of the diffusivity of the species that you're thinking about. So for example, for a fuel like hydrogen, very light, and it diffuses very, very fast, then the Lewis number is less than 1. And if you have a fuel which is very heavy, so a heptane or something like that, it diffuses very slowly, and the Lewis number will be larger than 1. So there'll be a mismatch when you get to the flame, and that will give rise to either a super or sub-adiabatic flame conditions. Yeah? Of course, because reactions are so dependent on temperature, this mismatch and this slight change in temperature would then lead to a secondary effect on the flame. So here's an example of a numerical simulation in 2D. This is the mass burned as a function of what's the Karlovitz number, here defined as the integral of the stretch along the preheat zone of the flame and weighted by the Lewis number. You can see for a methane air flame, where the methane has a Lewis number that's about 1, and this is a lean flame, so the fuel is the limiting reactant. We see that just by doing this mass loss, which is the first term in the right-hand side equation there, you get about right in terms of the decrease in mass as a function of this non-dimensionalized stretch. But there's a second term that will come in, which is the effect of that change on the temperature. And the temperature can be approximated using, let's say, one-step asymptotics as something of the order of the Lewis number minus 1 effect. So if Lewis number is exactly 1, that effect will not exist, and the flame would be, the temperature of the flame would be unaffected, and proportional to the amount of stretch that you have in the flow, non-dimensionalized appropriately by the flame time. So we see that that second effect will have an effect on the mass, and because I change the temperature, then I have to multiply it by a Zeldovich number, which is the number that is the sensitivity of the burning rate to changes in the burning gas temperature, right? So the interesting thing about this is that in general, the loss in mass, if you have positive strain, so these streamlines are going away from the flame, they will be always negative, but the second term can change the picture because the Lewis number, if it's very small, then the first term is now positive, and it can offset the picture from a negative loss to something that is positive. The over effect is usually talked about as Markstein number, because Markstein made these observations early on in the 50s and 60s, times a non-dimensionalized stretch. So we'll be referring to this picture on and on. So now you've done your experiments, you measured velocities, which are easy things to measure, and now you can obtain what the laminar flame speed is. And these are some of the pictures that you'd get of the different points. Each experimental point is a different stretch rate, which is on the x-axis, and then the laminar flame speed that you measure. And the slopes can be positive or negative, depending on the diffusivity or the relative diffusivity of the fuel. For some of the large fuels, the slopes could be negative or positive as well, depending on whether you're lean or rich, because if you're rich, now your limiting reactant is no longer the fuel, it will be the oxygen. So depending on the diffusivity of the oxygen relative to the bulk mixture, you can also change that overall picture. But this is how typically you measure flame speeds in this method. Okay, second method is you can arrange a ignition right in the middle of a large vessel. You seed it with tiny little particles, or maybe you just measure the rate of expansion there. And you can see here, in this case, for methane air, picture from Bruno Renou, and then you measure the rate of expansion of the flame. So naively, you might say, oh, that's the flame speed. But of course, as you can see, the tiny particles there, they're moving with the flame a little further ahead. And what we want is the relative velocity between the flame front and the unburned gas ahead of it. Measuring that, quite tricky, but possible. And I'll show you next an experiment that recently has been done trying to do just that. The idea here is that if you have just regular PIV, typically the interrogation volumes are relatively coarse, and you might not end up with the kind of resolution that you need ahead of the flame in order to measure those velocities. But a few years ago, the group at INSA Rouen also had some great success with changing the coordinates of doing the PIV analysis so they can get very, very good resolution of the PIV next to the flame. And that allows you to measure, as you can see on the right-hand side, resolutions of the order of pixels. So now you really can capture what's going on in that flame. So here are some direct measurements of displacement speed in a very nice paper by Marielle Cavell, who's here. And you can see here, these are both simulations on the left-hand side, and the circles are the individual points where velocities have been measured. The simulations show the purple line there is the temperature simulated. And you can see the simulations of velocity as it's rising up. And you can see the blow up of the very top there. You can match very well the velocity as simulated from direct numerical simulation of this expanding sphere and the velocity. And once you do that, now you have the relative velocity of the flame, which would be the top velocity just ahead of the burned gases. And then you can subtract the rate of expansion and the velocity that you just obtained, and then you get a laminar flame speed at each one of these stretch flames. Why is it stretched? Well, because you have now a balloon that's expanding, so now you have this stretch, which is proportional to the rate of change of the radius. And you can see both the simulations and the experiments all work very well, as it ought to, because, hey, you know, this is methane air. We should know at least that while we're doing that. But you still have to be very careful with how both you measure it and how you extrapolate these to zero stretch if you want a measure of the laminar flame speed. Now I'll talk about, I talked about the direct method. I'll talk about the most popular method, which is perhaps a little easier. You don't need to do PIV. And the idea here is that you measure just the flame front displacement, and you make a guess about the density ratio. And the idea here is to imagine that you have a displacement of an ISO curve. For example, if you have the burnt gases, then this weighted displacement speed would be on the right-hand side a rho of the unburned divided by the rho of the unburned, so that goes back to our direct method. And if you have the burned gas speed, then that becomes then the rho burned divided by rho unburned times the rate of displacement of the front minus the unburned gas speed. The reason why this is convenient is that, as you can see here in the simulation, on the left-hand side, as the flame expands, the burnt gas by symmetry stays put and just pushes the gas ahead of it. So now the unburned gas flame is zero, so at least I can measure the displacement speed relative to the unburned gas. So now we have these displacement speeds, SdB, by this indirect method. So what you need to do now is estimate the ratio of densities, which, if you assume equilibrium, perhaps not so hard, but of course this is a stretch flame, and now we could have slightly different temperatures ahead of the flame. Okay, so next we think about doing these nonlinear extrapolations of the velocity so that we can get the laminar flame speed at zero stretch. Here are some examples. This is a very nice paper from the group in Aachen and the group at ICAR in France, comparing both Schlieren methods as well as Niescatter, I think. And here we have the extrapolations. Typically, you can do just an extrapolation if the slopes are not very strong. You might exclude the regions that are affected by ignition, or if your radius is very large, which means at the left-hand side of the plot there, on the low stretch regions, and you exclude when the pressure starts going up, and then you extrapolate those points to zero stretch. For those three cases here, that looks not so bad, and you can extrapolate that and get reasonable results. But there are some cases here, and I'll talk to explain that, the equations in a moment, where on the right-hand side, you see a figure here where you have quite a lot of curvature. This is still methane, but rich. So if you try to do an extrapolation there, it looks like you could be in a lot of error because the slopes are quite large. So there's a related theory here, and I'll just motivate it. It's just very approximate. If you assume that the burned flame speed at the burned location is related exponentially to the change in temperature times the Zeldovich number, and as I showed you before, that there's an approximation for this temperature rise or fall as a function of differential diffusion, and you plug the bottom one into the top one, you get the strange looking so-called nonlinear equation, which was derived in a slightly different way originally by Severshinsky and Ronnie, and then popularized by Kelly and Law. And the idea is that now you are able to capture this whole curvature based of the stretch in this picture as shown. And typically you do that as a curve fit where the zero stretch of the burned flame speed and the SB naught and the Markstein length LB, which is the slope with stretch, are obtained from experimental results. The upshot of that is that now if you go to radius infinity and extrapolate that, then your stretch is zero for an infinitely large flame. And now you can get from the burnt flame, in principle, the laminar flame speed just by continuity, but only when stretch is 0. So I want to finish the section with a picture that will show you here. These are experimental data from Princeton and also simulations from their group, where what's shown here is the Karlovitz number, so a non-dimensional stretch on the x-axis, and then on the y-axis you have the normalized burn speed normalized to that obtained by doing a simulation with premix. Now you have these results, and the exercise here is to find out, when you do the extrapolation, how far off can you be. And you can see that if you extrapolate that, you get values, but they could be very far from the simulated value that you have with the detailed simulation. The detailed simulations go to 1, so that's good, because using that mechanism, they better go to 1 when you have 0 stretch. And they agree reasonably well with the models that you have. Now, if you try to do this nonlinear extrapolation, it's better than the linear extrapolation, but it may not still give you the right value. Now, if we do that with a different fuel, here with heptane, and the points now are actual simulations, and we are simulating the extrapolation, you can see that this is not so severe, that the extrapolations can get you within about 20% of the value that is considered, let's say, accepted at the moment for these fuels. The other observations that I wanted to make on this figure is that if you notice, for hydrogen flames which are lean, applying stretch makes it faster. Whereas for heptane, if you go lean, it makes the flame speed lower. Why is that? Well, that comes from that Lewis number -1 term that we were talking about. If you have high Lewis number for the fuel, so on the lean side, then that would lead to a negative term, which will make the first loss even more negative, so that all goes down. And in the case of the hydrogen, that term, the Lewis number now is very low, so the second term becomes very positive, and then you flip it to the right side. So just keep that in mind. Large fuels, lean, you have stretch, it goes down. Hydrogen, it goes crazy up, and that will come back a little bit later on. Okay, so that was the message that I wanted to give. Stretch and differential diffusion both affect flame temperature and the burning rate. The effect depends on the relative diffusivity of the deficient species, so if it's lean, that's the fuel. If you're rich, that's the oxygen. And in practical measurements, we have to be careful with these extrapolations. There will be uncertainties, they'll be creeping up, and these still persist, and they are related to differential diffusion typically. In the paper, I didn't have time to talk about that. There are actually few measurements at high pressure and temperatures, even though gas turbines and engines all work at high pressures and temperatures and so on. So there's quite a lot more work that ought to be done on this front. Now I'll make a detour into intrinsic flame instabilities, and these are not the flame instabilities that you heard about a couple of days ago, which were thermoacoustic instabilities. These are thermodiffusive flame instabilities, and they're very much connected to the differential diffusion between the controlling species and the fuel. A lot of good work, again, out of Princeton, as well as by Moshe Metalon, who I think is here somewhere, on the topic. And here's an example of a flame ball, which grows, starts very nice and smooth, and as it goes, a function of time. And at some point, stretches low enough, and then it develops monkeypox or something, it gets these little bumps on the flame. Why is that happening? Well, those instabilities depend very intimately on the Lewis number and the stretch of the flame. Here's some additional example of hydrogen flame at either lean conditions or rich conditions. The lean condition, very prone to these thermodiffusive instabilities, when Lewis number is less than 1. But if you go to the rich side, now the diffusive species is oxygen, and the picture changes, and you can produce these smooth flames. If you go to propane, this flips, because now you have these very smooth flames in the case of lean flames. And on the rich side, now you have the Lewis number of the deficient reactant, oxygen, being less than 1, and that is what creates these little cells. Now, of course, when we are running propane flames rich, for example, in an engine, you wouldn't go this rich probably, but This is actually happening, and we ignore it. That's not in the canon of what we talk about. So a lot more work, even with regular fuels, that needs to be done. I'll just give you a flavor of how this theory goes. If you try to understand what is the onset of these instabilities, you think about something that's flat, and you apply a little wave to it with a certain pitch, so a certain wave number, and then you find, will this perturbation grow or not, based on essentially modified Euler equations. And the equations are just too complicated. I must confess, I didn't try to rederive that. But you do end up with something that's very neat in terms of determining where the instabilities are. The top equation gives the growth rate of, in the case of a flat flame, and there are similar analysis for both a spherical flame and a stretch flame, where the first term here in this equation is the Dario-Orlando analysis of just a flame, and is it stable or not. And that first term only depends on the density ratio. And in principle, this would mean that a flame is always unstable, so the growth rate is always larger than, larger than 0. But there are other terms that creep up, and not surprisingly, now that I've told you something about differential diffusion before, is that they'll be proportional to the Lewis number minus 1 times Zeldovich, and that can stabilize the flame. You notice that the first term is proportional to the wave number, so linear with the wave number, and the second one is negative and proportional to the wave number square. So that then allows the flame to be actually stabilized. The various coefficients there can be also a function of stretch. And that means that you have a zone where the flame can be stable. So if you green on the lower hand side, there will be a point there where you cross 0, or conversely, you can reach a stretch rate where you go from a subcritical number to something that is critical, and at that stretch rate, you cross the boundary there of stability, and the flame goes unstable. So it's a combination of thermal expansion, differential diffusion, and stretch that would determine stability, and in general, positive stretch acts as a stabilizer. Here's another example of transition to instability in hydrogen propane flames, and I wanted to show you how the theory agrees reasonably well with the predictions. You can see here the hydrogen flames very quickly on the left-hand side go unstable, and the propane flames are very stable, and once you mix the two of them, then you have something in between, and predicting that something in between depends on predicting what the flame is doing and what the critical Lewis number is. In the case of the stretch flame, this theory is usually written in a slightly different form as a Pecklin number. The Pecklin number is essentially proportional to the radius of the flame at the critical point divided by the laminar flame speed. And as you can see, there's one term that would depend on the expansion, and the second term would depends on the Lewis number. And you can see that the theory predicts the onset reasonably well, not perfectly, because of course this is typically a linear theory and all sorts of very nonlinear things happening in this flame. The second observation is that, as you can see here, that the criticality condition is given as the radius divided by the laminar flame speed, and the laminar flame speed goes down with pressure. So as you go to higher and higher pressures, then the transition to instability becomes more likely, because your radius is going to be much smaller, and there will be a transition to that. And I'll finish this section by showing some very nice work that was done by Andy Aspden, where they took a number of DNS simulations looking at where in the pressure and equivalence ratio you might be at this critical point, or in this case, looking at the maximum rate of growth instabilities, this omega term there, and going along the ridge divides things that are very unstable and things that are not so unstable. And as I'll come back a little bit later, what you're looking at here is the fuel consumption rate of a hydrogen flame that originally started under laminar conditions, and then it goes crazy. And not only that, the rate of consumption, which are the white regions there is very, very high at the leading edge. And we'll see that over and over, and there have been several papers at this meeting where we've seen that, again, how hydrogen is a special case. So now I'll switch to measuring turbulent flame speed. It should be the same as a laminar flame speed, but now you're averaging that in ensemble space. And for an idealized steady planar turbulent flame, you would have a variety of different terms, but if you integrate that, then you just have that the mass that comes in has to be equal to the total amount that's reacted on the other side. How that happened, of course, inside the flame, it's a little bit complicated. Now, we measure these flame speeds typically to know something about turbulent combustion models, and typically we're looking for the simplest situation to inform turbulence closures. But doing that is not so simple because flames are not flat. Here's a statistically steady Bunsen flame, and another one which is a flame ball growing under turbulent conditions. And so we can't operate with these very simple paradigms of flat flames. So we have here typically turbulent flame measurements either in Bunsen burners or spherically expanding flames. They both are envelope flames, as in everything that goes in burns, so that makes it easy to work out the burning rate per unit area that you have. The Bunsen flames are statistically steady, so that's very good for optical diagnostics and is also representative of burners. The bad thing from the point of view of analysis, that is very non-isotropic spatial distribution of what's going on with the flame, and not sufficient analysis perhaps has been done of that. In the case of the spherically expanding flame, this is also an envelope flame, very symmetric, isotropic, and is also representative of premixed engines, but of course is unsteady. So trying to stick some lasers that work and give you species profiles and so on, not quite possible. So we need a mix of the two to try to understand everything that's going on. Typically, in turbulent flame speeds, this is done via a global measurement. So I have so much mass going in, and then I try to make the measurement of the area and how much burned per unit area. But of course, that doesn't account for the variations around the flame location, and ideally, we should be measuring locally around the flame. But I'll show you now how various measurements from a variety of different people across the ages there agree or don't agree, because that's very convenient. If we take the halfway point along the flame brush, this is the area of the progress of reaction, C is equal to 0.5. Oddly, that's usually divided by the unburned gas density rather than some weighted gas density. But it's convenient, but it doesn't correspond to the actual displacement speed anywhere. And here I'm plotting a whole host of data here on the lean side from a number of you who produced the great data there as a function of U prime of SL and the log of the integral length scale. And generously, I'd say they don't agree. Yeah? Why might that be? In general, they all go with somewhere the U prime over 1/2, a little bit more, a little bit less. But there's no coherent agreement of all of these flames. Why might that be? Well, there are large differences in burning rate around the flame. So if you take the average flame speed, and that depends on the distribution, perhaps it's not so surprising that it should give different results. There may be 3D effects. We're measuring a lot of the flames in 2D, and there might be different reaction rates for different L over D geometries and operating conditions. There might also be differential diffusion effects, even though most of these are lean methane flames. Lean and rich sensitivities are different. And finally, from some of these very tall, very intense flames, we're no longer in a flame-lit regime, and maybe different things are happening. And of course, there has been great work by Driscoll and others on that front. Okay. In connection with these Bunsen flames, one of the things that people can measure is the total area of the turbulent flame using B-scatter or OH PLIF. And so if you measure that total area, assuming symmetry from the 2D to the 3D, then we have an indicator here, which is the ratio of what you think went in and what you think burned. So that's the m dot divided by rho SL times the measured area burned. And if we plot that as a function of Karlovitz's number here, that seems to be quite a discrepancy. Instead of everything being equal to 1, it goes up to factors of 5, depending on which experiments you take. So there's a burning rate that's unaccounted for. One thing that you might think about is, well, how about 3D? Here we're measuring things in 2D and then extrapolating. Would that be a factor? We've done that recently in the lab. There was a paper on Monday where we tried to do that, where we measure both the vertical and the horizontal flame surface density and then integrate that. But the integrated 3D area, at least on these experiments, seems to account for maybe 15 or 20%. We haven't done it at very high turbulence, but it doesn't look like it's a factor of 5 to account for that. So that's still a mystery that needs to be worked out. I think we need to work more closely together and save the original data so that we examine also the velocities and perhaps even 3D areas in these very turbulent flames. Now, switching to spherically propagating flames. Now we have a slightly different picture. We have on the inner side the burned gas, on the outer side the unburned gas. So if you draw a little circle around that flame, around the leading edge, for example, we can define that as the propagating speed of the flame front. And the balance of the progress of reaction would look like something like this. The amount burned is then proportional to the volume of that ball that grows. And then if you want to define now a flame turbulent speed, then by mass conservation, you equate the mass coming into the flame of reactants to the mass burned. And if you take that interface to be that sphere or that interface, then you have then also pockets of mass that are not burned within that sphere. By kinematics, you could have this direct method of measuring, if you could, by measuring the rate of displacement of the flame minus the unburned flame speed. But of course, too hard. Nobody has done that yet. I think people have made measurements of the U sub U, but not put everything together. So more work still to be done on that. And both of those factors are difficult to measure. So what's done in practice is, let's just take something about in the middle. It's Schlieren. We take the peak signal there it's somewhere in the middle between the fully burned and the unburned side. And then we use the indirect method, essentially, of measuring the turbulent burning rate as weighted by the density there. And when you do that, now you get the turbulent flame. These are data from Taiwan and data from Princeton on the right-hand side. And they all kind of go the same way. They go with about the radius to about power of 1/2. And the turbulence also with a power of 1/2. So people like to say that it goes as Reynolds number to the 1/2 power. Now, interestingly, a lot of this data through history has been reported as the turbulent flame speed as a function of U prime, which obviously is difficult to interpret because it varies with radius. So if you don't tell me what radius that is, I won't be able to use a model to try to compare that to. And only relative comparisons are possible. Now, why is it that it varies with time and radius? There have been only a few select measurements of, for example, me-scatter profiles. On the left-hand side, you see, or the right-hand side, the left-hand side picture, you see me-scatter profiles there by Bradley. And on the right-hand side, by Brunet-Renou in a tunnel. And coming back to the left-hand side, we see that, by and large, most measurements agree with this trend of, it goes with Reynolds numbers to the 1/2. But there's some outliers, and this is already filtered, only methane at ambient conditions. If we think about why does it grow with radius? Well, several things are changing, but if you do a balance, you'll find that the ST over S naught on the last equation there should be equal to some type of flame surface density times the flame brush. Now, the flame brush is growing with radius, with time and with radius, so there might be one reason why it grows with the 1/2 picture. And unfortunately, there haven't been very many measurements of the second term, which is the amount of unburned mass, which I did not account for. So quite a lot of work still that we could be doing with more sophisticated diagnostics. Why does it grow then with the 1/2 power? Well, a very likely explanation is that this is turbulent or Taylor random walk processes that then go as the radius increases. You expect that the turbulent flame brush would increase in size. But there has also been the suggestion that hydrodynamic instabilities or even thermodiffusion instabilities may play a role on that. And this is very much an active area of research that hasn't been resolved. There are very few detailed measurements of the flame brush growth, actually, or anything else in these very unsteady flames because it's very hard. But I'll show you some of these measurements that I showed you in the beginning of the methane flame, where here the flame speed was measured, as well as the flame area in 3D was measured, some very, very nice experiments. And then this I0 factor, which is the ratio of what you think it should be burning if everything is burning at the laminar flame speed that you know, to that of the area that you measured. And perhaps generously, these numbers, in my view, hover around 1 because the uncertainties are maybe of the order of 30%. But if you take the measurements of hydrogen, wow, what's going on here? Yeah? So I measure the area and I measure the growth rate, and the growth rate still exceeds the area that I have. So that's something that's going on to the usual unstretched flame speed. And now I don't have to tell you, because you already guessed, what's happening is differential diffusion. So let's now take a look at what DNS tells us about that. But before I do that, I wanted to show you this experiment, which has been a little bit buried in the literature, but is a very, very nice experiment. And then Andrei Lipatnikov said people in Russia did that many years ago in the 1980s. And indeed, they had. Perhaps they weren't so extensive, but still illustrated the purpose. But here I'm showing some experiments that were done by the group of Buckhorn. You take just a bog standard turbulent flame speed of methane, and you burn it either lean or rich, but you start at a composition where the laminar flame speed is the same. Yeah? So if you don't do differential diffusion, if you don't think about that, they should grow at the same rate. And they do when there's no difference in the differential diffusion, which is the right-hand side near stoichiometric. So here, similar Markstein number, which is the slope with stretch, they burn at the same rate. If not, they will burn at very different rates. If you have the lean, that will go very fast, and if you have the rich, you'll go much slower. If you take another bog standard fuel, which is propane, and you start again at the same burning speed, you have the same thing that happens at stoichiometric, around near stoichiometric on the right-hand side. But on the left-hand side, you see that there's a flipping. Now the rich is on top, and the lean is on the bottom. What's happening there? Differential diffusion, right? And that is expressed by this Markstein number. So in general, if you have low or negative Markstein number, so these are the light fuels on the lean side or oxygen on the rich side, this is an accelerator for turbulence. And if you have the opposite, so very large Markstein numbers, that will be your brake. Okay, DNS, does that see what we see in the experiments? Yes, good. This is a collection of DNS simulations that were done over the years by the groups by Andy Ashton, the group at Caltech, and Vinod's group. You can see here for methane, which is the middle one, as a function of Karlovitz number, so that's the turbulence going up. We see that the turbulent flame speed is, middle affected by turbulence. These are all lean, by the way. If you go to a fuel like hydrogen, now we know why. This is going very, very fast as a function of turbulence, very sensitive to turbulence. And then if you go to other bog standard fuels, such as heptane and octane, not too much change. Very difficult to get them to go. Yeah? And this seems to be quite consistent across the different experiments. So now let's take a look at what the snapshots look like if you have methane burning. Yeah, turbulence, reaction rates, OH, those are very well known. They're all in the same place. If we take hydrogen, the world has gone crazy. You have all these little fingers extending into the reactant zone. And the burning rate is highest whenever you have these very high curvatures. And I think we've seen at least 2 or 3 papers in this meeting with similar predictions. And that's because we have differential diffusion and everything is enhanced by positive curvature. If we have a very large fuel, in this case dodecane, yeah, this is not going anywhere. Yeah? So we try to accelerate it with turbulence, but it gets killed off by the wrong kind of differential diffusion. So curvature actually slows things down. You can get a little bit of an acceleration at the trailing edge, but it doesn't really go anywhere. And that is very much reflected then on this picture of low Lewis number, negative Markstein, leading edge accelerates, things go unstable, and vice versa. This is very much reflected in the conditioned flame speed versus curvature. This has been done in DNS with perhaps less resolved chemical mechanisms, and these are with the full mechanism here, Karlovitz number of 36, so moderate turbulence. And you can see the middle one, which is methane. There is a slope, a negative slope, as you might expect from negative Markstein's number, but it's nothing to write home about, which is why we've been doing simulations of methane quite simply and it still works okay. If you go to hydrogen, you can see that these slopes are much more severe and they're asymmetric. So the positive curvature seems to affect a lot more than the negative curvature. And if you go to dodecane, a large fuel, nah, yeah, doesn't really matter, which perhaps is good because that means that you can do simulations of these fuels, and it kind of works if you do just something that's flamelit and you don't worry about anything else. I'm getting to the end of the talk. Here's the conditioned fuel consumption for different Lewis number. Not surprisingly here in the state space, this is the fuel consumption rate as a function of temperature relative to the red line, which is the laminar. For hydrogen, it's very much increased by turbulence. For dodecane, it's decreased by turbulence on a per volume basis. And for methane, that is unchanged. Do models out there incorporate differential diffusion? Well, of course, differential diffusion is everywhere. If you calculate a flame, it has differential diffusion in it with all the intermediates and so on. But perhaps nothing special about the role of stretch and curvature. But throughout the literature, there have been some efforts, and in the paper you can find some references to that, where, for example, you might correct the laminar flame speed to a weighted flame speed, which is a function of the expected mean curvatures or mean stretch that you might have in the flame. Sometimes it's done with Karlovitz numbers, sometimes with Karlovitz and Markstein numbers. And you can also have a submodel adaptation of LES, for example, using DNS results. Here are some results from Chakraborty and Kant from a number of years ago, where you correct a model based on the flame surface density, or you can have, for example, an efficiency function, such as the one on the picture that you show, where the efficiency function of the averaging that you do in LES is a function also of the Lewis number and the size of your grid. So more of that probably will be coming up as we get to further studies. So in summary, how fast can we burn? Well, much faster than expected when the Lewis number is less than 1, and not so fast. Otherwise, you can push your turbulence and it won't necessarily burn as fast as you wish it would go. And that is due to the microscale of the flame, the role of stretch and differential diffusion. Instabilities are present under normal operating conditions, and there may be an interaction between these differential diffusion effects and the flame wanting to go unstable and how it interacts with turbulence. That has yet to be codified into turbulence codes and so on, and we don't know just how important that is. But what you do know is that if we're going to be using hydrogen, then a lot of things will have to change or have to be made better to take into account all of these different effects. But one of the things that I became much more aware of as I was going through preparing this presentation is actually there's a gold mine of data there. You know, for example, the experiments you do rich and lean methane, and all sorts of different things happen. So if people were just to save their data so we could reanalyze that with new eyes, it would be brilliant. So that's my recommendation for the future. Save all of the raw data, please. Put it somewhere so we can go back. Don't lose their hard drive because they could come in and be very useful for people looking at the data and not having to scan things and extract the data, as well as incomplete data that we have where the data has already been processed. So we should continue to do more experiments, a range of fuel mixtures, and explore all of these issues. Now that we have better diagnostics, maybe do even 3D mapping of that. We should look at combustion instabilities as well and see how that and turbulence connect. And extend that to the non-unity Lewis numbers, which would be very important. I wanted to say thank you to all of my students who help and postdocs who help the lab keep in touch. You can see that in our day-to-day garb at Cambridge doing science. EPSRC, which is our funder for all the basic work that we do. University of Cambridge for giving me time for thinking about all of this. I'm also indebted to all the people who provided me with a lot of figures and some of the reviewers who gave me 20 pages of comments, and that was very, very helpful. And to all of you who write great papers in combustion, so carry on. Thank you very much.
Thanks a lot, Simone, for this very stimulating talk. So it's my pleasure to hand over